Hello everyone, and welcome to this special webinar with Canary Systems and Mining Magazine, which looks at effective risk management for tailings facilities. My name is Alva Goodbody, the Americas editor of Mining Magazine, and it's a pleasure to be with you today to discuss this important topic. Before we start, I just want to remind all of our listeners that this is an interactive webinar, so you'll see a light blue button on your screen that you can click to ask a question, and you can do this at any point during the event. If you have any technical problems during the event, you can also click the red button marked Live Event Tech Support, and our team will get back to you as quickly as possible. In addition, the audio recording and the slides from this webinar will be available on the Mining Magazine website for all registrants in a few days. So with us today, we have Alex Mewert, President of Canary Systems, with us. Alex is an excellent high-caliber speaker who's ready to talk all about effective monitoring methodologies for tailings facilities. Alex Mewert has over 30 years of electronics and software development as well as field experience in data acquisition and control. As president of Canary Systems for over 20 years, he has designed and overseen effective risk management solutions for tailings facilities at dozens of mines. He has developed in whole or in part many types of hardware and software products for use in the field of data acquisition, including data loggers, signal conditioning products for numerous types of instruments, with a specialty in vibrating wire instrumentation and software. His areas of expertise also include system integration and telemetry, whether wired or wireless. This webinar will outline several methods for external and internal monitoring of tailings facilities and will outline their strengths and weaknesses. We will also open for questions and answer them after the presentation. So I'm going to hand over to Alex now to start this presentation.
Thank you, Alva, for the introduction. I got started in this business through working at a company that manufactures instrumentation. One of the interesting characteristics I saw with many of the project sites that I visited was limited value from the installation of instrumentation. So in other words, instruments were installed, but then there wasn't really a program for collecting data, for reviewing the data, for understanding the data in effective ways. That was the basis for starting Canary Systems over 20 years ago now, to really focus on how to help clients realize the maximum value from their instrumentation investment. And in this context, of course, it's about risk management. Tailings facilities have a long history of catastrophic failure, most of them in the mining industry. Most recently, there was a terrible failure in Brazil by one of the large mining companies. Tailings impoundment collapsed and wiped out not just the mining operations, but also a village. I think at last count, somewhere in the mid-200s of fatalities. So this has underscored the importance of effective risk management for tailings facilities in particular. So the presentation we've put together today is really just an overview of the different types of instruments that we see commonly used or we recommend for tailings monitoring. And then we'll wrap up the discussion with a presentation of our software platform, which is also a critical part of the system. So again, it's one thing to install instruments, but it's another to have an effective software system or a platform, as we like to call it, to help understand what that data means in the context of risk management, and ultimately to prevent these catastrophes like we saw in Brazil earlier this year. We have a lot of material to present, so I'm going to go through these slides fairly quickly. We'll start with just a general presentation of what we're trying to accomplish in monitoring of tailings facilities. In recent years, there's been a lot of focus on looking at external deformation for managing managing risk or monitoring tailings facilities. But we're actually going to start this discussion talking about internal types of monitoring. So really, an effective tailings monitoring strategy has to have internal as well as external monitoring. In general, your internal monitoring provides for deformation, load, and pore pressure or internal water pressure. External monitoring also provides for deformation, for leakage. The reason why internal monitoring is so critical is that it provides leading indicators of failure. So in other words, when you start to see external deformation, it's really just a consequence of internal failure developing. And so that's why the internal instrumentation is so important, because it gives you more time to provide for mitigation. So for example, think about pore pressure. There's some pretty dramatic videos of this tailings dam failure in Brazil. One that's a straight view of the dam actually failing. And you can see it's a classic liquefaction failure, meaning the soils that were impounding this tailings material were saturated, they lose all their strength, and then it fails to impound the material. Well, internal water pressure or pore pressure monitoring would have provided a pretty substantial leading indicator, which would allow for time to then mitigate. So there's numerous methodologies that can be employed at that point to mitigate the failure, including installing depressurization wells, adding a buttress, or other changes to the design itself to mitigate that potential impending failure. So we'll look at, again, several types of technologies for both internal and external monitoring. We'll start with internal deformation. There's a couple of different types of technologies that we see commonly used. The first we'll talk about is in-place inclinometers. These are typically installed in the casings that are part of a manual inclinometer survey program. So this is a well-accepted practice in the field of embankment and tailings dam monitoring, where you essentially drill a hole in your tailings dam, you install a special grooved casing, and a torpedo with a very sensitive set of inclinometers is run up and down this casing to profile the tilt of the casing. So over time, as that internal deformation acts on the impoundment, you can compare these sets of inclination data and be able to understand where failures are happening internally, and also, more importantly, the rate at which those failures are occurring. One of the interesting phenomena we see with tailings data, and really all deformation monitoring data, is that generally you always have some sort of failure or some sort of movement, I should say, or deformation. So what's critical then is to be looking at the rates of that failure or rates of that deformation. In other words, it's not necessarily a problem to have movement, but it is a problem if that movement is accelerating. And that's usually the indicator of a failure. So an in-place inclinometer essentially replaces the manual inclinometers. They provide for automation. The manual inclinometer survey can take a number of hours, and typically it's done very infrequently on a tailings impoundment, maybe even only once a year. An in-place system would provide for much more rapid data collection, as often as perhaps even once a minute. So not only can you identify the failure of the impoundment, but you can identify where in that impoundment, at what level, for example, the failures are potentially developing, and again, the rate at which they're occurring. One of the weaknesses of this in-place inclinometer system is that it is expensive. Anytime you have to bring drillers out on a tailings impoundment, there's significant costs incurred. So this tends to limit their deployment, especially for a large tailings impoundment. The related type of technology is called a shape accelerometer array. The traditional in-place inclinometer is a bit of a challenge to install. It requires a lot of assembly in the field. You have sections of tube and wheel assemblies that literally have to be put together like an erector set. The shape accelerometer array, it's a patented technology sold by a company in Canada. It's become very popular for tailings impoundment monitoring because it comes, as you can see in the picture, it comes on a spool. So you literally just unspool it into a hole or into a casing, And it essentially provides that same type of data as the in-place inclinometer, but in a much easier to install model. It also provides much better discretion typically. So with an in-place inclinometer system, you might have a 3-meter gauge length. So in other words, from one sensor to another in your casing might be 3 meters. With the shape accelerometer array, the standard gauge length is a 0.5 meter. So it allows for more discretion to identify where in the impoundment internally you potentially have movement and potentially have a developing failure. Again, like the in-place inclinometers, one of the weaknesses is they're expensive. In fact, they're more expensive than the traditional in-place inclinometer. So that again tends to limit their deployment on projects. And again, you have to drill a hole. So anytime you have a driller out there, there's significant cost incurred. Another method for internal deformation is settlement sensors. So these provide direct measurement of vertical stability. So over time, any type of embankment will slump. And the settlement system will provide for characterizing that slumping or that deformation over time, that vertical deformation over time. You can achieve very high resolution, even down to some of the systems on the market are down to 1 millimeter or better. And you can have very high range as well. So greater than 30-meter range is possible. One of the challenges with the settlement sensors is that they generally do have to be installed during construction. So it's not typically an instrument that can be installed. There are some versions that can be installed after construction, but the best design really would incorporate these sensors from the installation or from the construction, I should say, of the tailings impoundment itself. And in mining, that's generally not too difficult because the tailings impoundments tend to be very dynamic. They're built up over time. So over time, at different levels, these settlement systems can be built in and provide for that vertical deformation monitoring from that level, from that time forward at that level in the tailings impoundment. They are a little bit tricky to install. As you can imagine, you're installing a sensor, and then you have to provide for a special kind of internal conduit, if you will, like a protective conduit, which is usually it's usually constructed using a trench with sand or other material that provides some protection for the cable and the tubes. So unless there's careful attention to making sure that you don't actually build a leakage path into your tailings impoundment, you could have potential issues with basically causing leakage of your tailings facility over time. Another type of internal deformation sensor, you could call it an internal load sensor, is a pressure cell. These are very popular as well to essentially measure the weight above a sensor location. This weight can be a reflection of the saturation of the material that's above the sensor. So this also can provide a way to characterize migration of water in that tailings impoundment or that tailings embankment. Again, these are typically installed. During construction. One of the other advantages with pressure cells is that they provide for dynamic loading. So, in other words, as a facility is built up, you can characterize the increases of loads in that embankment over time. Again, similar to the settlement sensors, you have to be careful with installation to not create leakage paths. You need to take care of your cables. Many tailings impoundments or embankments can be subject to pretty substantial deformation. So obviously, if you don't protect the cable, then you'll have breakage of the cable, which obviously means you lose that sensor. And again, they have to be generally installed during construction. Probably the most important system for internal monitoring of tailings impoundments or tailings embankments is pore pressure. And this is generally done through piezometers. There's a couple of different methods for installation of them. They can involve actually installing a pipe and then putting an instrument inside the pipe. The pipe has a filter assembly at the bottom, which allows you to capture the pore pressure at a certain elevation. The other method that's become more popular in recent years is called the grouted-in method, where you drill a hole in your embankment and you install the instrument, and then you fill that hole with a permeable grout. And so it avoids some of the complications from the pipe installation, the potential leakage paths and other challenges with pipe installation. Internal hydraulic pressure is key to the stability of an embankment, because water is what essentially weakens the embankment and causes failure. So the better you can characterize those internal hydraulic pressures, the better you can be aware of potential failure modes developing. In other words, a pile of material that's dry is not going to go anywhere. It will remain static. But as soon as you add water to it, you'll create a potential failure mode. So that's why measuring those internal hydraulic or pore pressures is so critical to long-term risk management for a tailings facility. And also, if pressures start developing that are beyond design limits, various methods can be employed to reduce those pressures. And so again, having instruments that can measure that internal hydraulic pressure can allow you to characterize how well your depressurization efforts are working. Obviously, without instrumentation of this type, it'll be very difficult to understand. For example, if you're installing a pumping well to reduce internal pressure, without these instruments, it'll be difficult to understand how well that depressurization effort is working. Some of the weaknesses, generally you have pore pressure measurement at a discrete elevation in your impoundment. So that's a weakness, because due to how these tailings impoundments are built up over time, you have essentially like internal stratigraphy. So in other words, the materials are not consistent from one level to another. So this leads to kind of interesting paths for water or pressure to migrate internally. So if you're only measuring at a certain elevation, it can be difficult to understand what the pressures are at other elevations within the embankment. In fact, in many cases where there are failures of tailings impoundments, it's because the pressure was built in an elevation that was maybe unanticipated. And so this is one of the challenges with piezometers, is being able to measure that entire column of hydraulic pressure. The different manufacturers has come up with solutions for this. For example, they have so-called nested piezometers, where they actually will string a bunch of instruments together along one cable, and you can essentially then have a little bit more discretion in profiling the column of hydraulic pressure. You can install multiple wells in a given area, with each well or each borehole at a different depth, and then a sensor gets installed at these different depths. But as you can imagine, you're drilling now more than one hole, so the cost escalates. And then one of the other key weaknesses is that it doesn't measure deformation. So you're really just measuring the internal hydraulic pressure or internal pore pressure, and that doesn't necessarily relate directly to deformation itself or movement of the tailings impoundment. Oftentimes there is a relationship between the two, but not in all cases, so you have to be careful. Okay, now we'll transition to some technologies for external deformation. So in other words, when you're looking at your tailings impoundment, how do you characterize how much it's moving? And there's several technologies that are available in the market now. The first we'll talk about is satellite radar, or InSAR. So, of course, most people are familiar with how radar technology works. You bounce a radio signal out into space, and you get reflections back wherever those waves intercept an object. Well, the same principle is applied for satellite-based radar, where you have satellites that are flying around the Earth at different intervals. They're bouncing these radio waves off the surface of the Earth, and you're getting reflections back. And by comparing one set of those reflections to another set, you can calculate deformation. Now, this requires quite a bit of data processing. There's a number of specialty companies that have appeared on the market in recent years to provide these deformation monitoring services. One of the tricks with this service and with the data is to register these data sets. So in other words, when you're getting two sets of reflections from the Earth, how do you actually align these two sets of data so that you can determine the movement for a given area? So that's where most of these firms have developed proprietary technology. They've come up with methodologies to provide for this so-called registration, and then to have different ways to then validate that. One of the strengths of InSAR is that you can cover quite a large area. One of the service providers that we work with, they have a couple different service plans, but one of their coverage area plans, I believe, is a 20 square kilometer plan, so something like 4 by 5 kilometers. So that gives you, in many cases, the coverage not just for the tailings impoundment, but coverage for an entire mining operation. It's also unaffected by weather. When you look at InSAR data on a point basis, meaning for this 20 square kilometer area, the number of points that you're actually being provided for deformation, it ends up being pretty inexpensive. And the discretion is pretty amazing when you think about how, these satellites are thousands of miles above the Earth, and yet they're able to resolve down to even sub-millimeter for deformation over that large coverage area. The primary weakness of the InSAR, or the satellite-based radar, is it's not really suitable to dynamic monitoring, because the frequency of the data sets is a function of how often the satellites are rotating around the Earth. And those intervals can vary between 1 and 11 days, depending on which satellites you're using, which part of the Earth you're trying to cover. So obviously for dynamic monitoring, that's a bit of a limitation. There are more and more satellites being launched every year with these capabilities. So I think over time we'll see a reduction in this latency, and perhaps in the near future, this will be a good option for dynamic monitoring. Perhaps, once data sets can start to be processed and delivered, say, twice a day, I think it becomes very viable as a dynamic or real-time monitoring tool. In the meantime, we have ground-based radar. So there are several companies around the world making ground-based radar. So essentially the same technology as InSAR, but with an apparatus that's actually installed facing a tailings impoundment or on the facility. This provides much more dynamic monitoring. Typically these radars can scan a facility every 30 minutes, sometimes even faster. So for real-time monitoring, a much better solution compared to the satellite-based radar. So we've seen the adoption of ground-based radar in particular for our mining clients and for tailings. Not so much in tailings impoundments, but I do believe we'll see a trend towards this in the future. It provides much better, or I should say, of the two types of radar, provides higher resolution compared to the satellite based radar, very accurate down to sub-millimeter. And the systems have been on the market now for a number of years. So they've kind of worked out the kinks. And even though it's a very sophisticated platform, most of these systems came out of defense projects originally. We've seen pretty good reliability in recent years with the equipment that's on the market. One of the weaknesses, depending on what the line of sight looks like, you can have difficulty characterizing some types of failures. And likewise, this is not a movement direction technology, so it can be difficult to determine in what direction movement is actually occurring. Imagine a slope that's just sliding down. Okay, so in what direction is it moving? Because the slope basically looks the same from one set of data to another. So that's one of the challenges with the radar. The radar will identify that the slope is moving, but it can often have difficulty understanding in what direction and even the magnitude of that failure. One advantage not mentioned compared to the satellite InSAR with the ground-based radar, you have better characterization of vertical surfaces. I would say this is one of the weaknesses of the satellite-based radar is you're looking at the surfaces with a fairly steep angle. So it can be very difficult for satellite-based radar to characterize vertical movement. It's very good with horizontal, but it has a difficult time, or I should say, it has a difficult time with horizontal movement. Sorry, not vertical. It's actually very good vertically because you have a fairly steep angle that you're looking at, but the horizontal movements or the facing movements can be difficult to characterize with the satellite-based radar. With ground-based radar, since you're situating this radar facing a slope, you have very good horizontal deformation characterization. And conversely, you also have limited vertical deformation. So we see many of our mining clients really adopting both technologies for deformation monitoring. The satellite-based InSAR to provide that large coverage area to provide for vertical deformation characterization, the ground-based radar to provide more localized real-time monitoring that gives you horizontal displacements. Another technology that we are seeing more adoption of, especially for tailings monitoring, is GPS. We all know about the global positioning system satellites that are available. All of our cell phones have this. This is how, Google Maps can show us, where we are and how we get from point A to point B. Likewise, the same technology can be used for deformation monitoring. GPS on its own has pretty poor resolution, down to maybe a few meters. Obviously, for deformation monitoring, that's not adequate. The type of GPS that allows for millimeter accuracy is called differential GPS. So this is where on a given tailings facility, you have a reference station. So it's a GPS receiver located in an area that's considered stable, and this can be confirmed by surveying or other methods. And then you have on the tailings facility itself a number of GPS receivers. And so by comparing the satellite data between those GPS receivers that are on the tailings impoundment itself against the base station, you can then determine deformation. So essentially, the difference between those two data sets is the change that can be potentially occurring over time. And again, this differential technique has been well tested. The algorithms have been developed over several decades now and work very well to provide even down to millimeter resolution. There have been some developments in recent years. We came out with a much lower cost GPS receiver that's specifically for deformation monitoring. And I do believe in general we'll see more adoption of GPS for external deformation monitoring compared to some other technologies that are out there. One of the advantages with GPS over both InSAR and ground-based radar is that it's very fast to deploy it. So you can identify a failure area or a high risk area, and within an hour or two, whatever it takes really to drive out to the facility and connect some cables together, install an antenna. So perhaps a half a day to get a monitoring station installed to provide this high quality deformation data. Also, it measures in all three dimensions. So both, again, ground-based and satellite-based radar are both limited in different ways in terms of how they can characterize deformation. But with GPS, you actually get true XYZ measurements. So you actually can see in 3D space where and how movement is occurring. And you can also have vectors and or direction of movement as well, which is critical to deformation monitoring. Again, it's true 3D data, whereas both ground-based radar and satellite-based radar, it's essentially like quasi 3D. You have 3 dimensions, but you have to consider some grains of salt with some of those dimensions. The weakness is it's still relatively high cost per point, especially when you compare to ground-based or satellite-based radar. The individual sets of electronics, obviously, if you're comparing the cost of one GPS station to a ground-based radar, the ground-based radar is much more expensive to purchase and install. So with the ground-based radar, though, when you look at it on a per point basis, the average cost of each deformation monitoring point is very low. Whereas again, with GPS, you have a relatively high per point cost. But again, where you're looking to rapidly deploy a deformation monitoring solution where you've identified a high risk area, it's a great solution for tailings monitoring. We haven't seen too much adoption yet of robotic total stations, but I do believe in the future we'll see more application of these. These are used pretty extensively in other aspects of the mining operations, particularly in open pits. Robotic total stations are essentially the survey instrument that we see surveyors using oftentimes along the highways to update the highway maps and survey plans for construction. The robotic total station is essentially a automated version of that same device. It's a theodolite, so it's a device that measures very accurately angles and distance. So you're shooting a laser to a reflective target, and based on the angles and the distance to that target, you can then compare one set of these angles and distance measurements to another, and over time characterize deformation. So essentially, that target becomes a point in 3D space that you can measure with this robotic total station. So in open pit mines, for example, we see robotic total stations used very extensively, where they'll install a robot or maybe 2 robots to provide coverage for a whole pit. They'll install a series of prisms on different ramps, slopes, high walls, benches, and automate the collection of data from all of those prisms. And again, each of those prisms becomes a point in 3D space that you can characterize over time. So as those points change because a ramp is failing or a slope is moving or a high wall is moving, you can then characterize those movements. Likewise in tailings, we are seeing adoption of robotic total stations for characterizing movements of tailings facilities. So in that case, the prisms would be installed generally on the faces of the tailings impoundments. The robotic total station would be installed facing the tailings impoundment, and then would be set up to automatically scan those different points. And again, provide you this XYZ or three-dimensional data over time. The ranges on the robotic total stations have increased quite a bit over time. The manufacturers have gotten really good at allowing these devices to work over longer and longer distances. It wasn't that long ago that the maximum distance might have been 500 meters. Now, most of the instruments on the market can go out to 3,000 meters or 3 kilometers, and some even further than that. So it's very easy then to cover a fairly large area with just one robotic total station. The points themselves are very inexpensive. It's basically just a reflective prism. So those are very easy to, and they're very easy to install. Generally, they get attached to a piece of steel rod and get driven in. Tailings impoundments in general tend to be pretty easy to work on because the impoundment itself is built generally from the tailings material, which is a fine mud that dries out. So it's very easy to install prisms, and again, with the long range capabilities of these robotic total stations, you can cover a pretty large tailings facility with just even a single robot. A couple of the weaknesses, because it is a laser, if you do have, for example, ground fog, well, it's light that's now trying to be pushed through particles of water. So that light beam gets deflected. And so atmosphere can be a challenge, especially in mining areas where weather is problematic. Obviously, in the desert or areas where you have better weather, you get better performance from the robotic total stations. But we have some clients that literally they're operating mines in jungles where there's rain, there's fog, there's cold, there's dust. All of these will degrade the performance of the robotic total station. And obviously, if it's severe enough, you may not even be able to collect data at all. The other challenge with robotic total stations is you do have to install this prism. So unlike a ground-based radar, which can just scan a slope, you have to install a prism wherever you want a 3D monitoring point. So depending on the construction of this tailings impoundment, there may be difficulty actually getting to locations where you need to install prisms. The tailings impoundment itself may have significant washouts. It may be difficult to travel by vehicle around the impoundment. There may be steep walls that are difficult to access or difficult to install these prisms on. So there can be some challenges with just the physical installation of this equipment. Another technology that's available in the market is what's called a wire extensometer. So it's a very simple device, but actually very effective, especially for where a high-risk area has been identified. So in other words, you have a slope that you know is failing, and you need to characterize more accurately the rate of failure. As I mentioned earlier, all these structures are failing. Everything is falling down over time. And so what becomes critical then is to characterize the rate at which these failures are occurring. This is where this wire extensometer can be very effective. Essentially, it's a wire that has a stake attached at one end and a optical encoder at the other end. So this wire is fed out from a spool, and as it's fed out from the spool, it rotates this optical encoder. The stake is installed in the downslope of a tailings dam. So as that slope is moving away from the spool of wire and the optical encoder, you have a rate of change. And so you can very accurately characterize then over time the rate at which this slope is failing. And that becomes a critical parameter in understanding the failure mechanism of a slope. They're relatively easy and quick to deploy. You can see in the picture here, it's basically just a box with some electronics in it. It can be installed very quickly, even just with some rocks holding it in place, as you see in the picture. The spool of wire and the optical encoder is all within this electronic box. So you basically just unspool the wire, attach it to a stake that you've driven into your slope, and now you can characterize that slope failure. And in terms of data collection frequency, can be as frequent as every minute. So you can actually have a very dynamic or low latency real-time monitoring system. Some of the weaknesses, it is a relatively expensive device. I think over time the cost of this equipment will reduce, but at present it's a fairly expensive piece of equipment to install. Again, critical locations may be inaccessible. You have to install a stake with a wire attached to it on the downslope of an unstable slope. So there may be restrictions on physically being on that slope if it's highly unstable, and so that means you can't install this instrument. And one of the other challenges is it's a wire that is strung from an electronics box with a spool and encoder down to a fixed location in your slope. So animals, many of the mines that we work on have large animals like deer. Any animals in the vicinity can interfere with the wire. Wires can even be broken. It's a steel wire, so it's fairly robust, but we've actually seen cases where they've been broken, probably by a large animal trying to run through and breaking or pulling the wire out of the stake it's attached to, or pulling the whole assembly over to. We've seen that before. Okay, so just as you can measure internal water pressure, weirs are an effective way to measure where water is actually coming out of your tailings impoundment. All tailings impoundments leak to some extent. That can vary depending on the design of the drainage, but in general, there's going to be some leakage. So it is important to characterize that leakage over time. And so we see many facilities with weirs installed. Generally, this is a set of drainage channels that terminates in a basin, and then that basin allows for exit of the water through a special gate or a weir. There's a couple different configurations for these weirs. You have so-called V-notch weirs, rectangular notch weirs, square notch weirs. The idea is that as the level of water in this basin rises, it rises as it exits as well, because the exit of the basin is through this specially formed gate. So you can then calculate the flow of water based on the level and on the characteristics of this gate. So it provides for essentially verification of your design. All embankment designs should include an allowance for leakage. And so by monitoring that with a weir, you can see how well your design conforms to the real world. And again, likewise, if you're seeing increases in, or you're seeing excessive leakage of your embankment, that can be indicative of internal failure. So basically, there's internal water paths developing that are either unanticipated or the result of construction or other factors, and that could be indicative of a potential failure mode developing for your tailings embankment. Some of the weaknesses, well, as you can imagine, it's a basin that collects water. So when it rains, the basin fills with water. So allowance has to be made for generally a fairly large amount of ingress from surface water, which is from rain. This can be minimized by how surface water is routed as it exits the embankment. But in general, there needs to be allowance for that ingress of water as a result of rain. And also, really for best design, the drainage, which then feeds water to this basin, should be part of the design of the embankment itself. This typically is not done. There generally is for tailings impoundments. There's a design for internal water collection, but we don't often see much of a design for external water collection. So it's important that this be part of the design of the facility. That concludes our discussion about monitoring technologies. There are a few others that are on the market, so don't consider this the comprehensive discussion of monitoring technologies. And we went through these technologies fairly quickly, so I'm sure there's a few details about application and installation that I didn't cover. Again, the purpose of this presentation is just to provide an overview of what's available on the market and how these different technologies work together to help manage risks. What's important to understand is that there isn't just one technology that solves all of the risk management challenges for these facilities. It's important to think in terms of all the different systems that are available, and then in reviewing a particular impoundment or facility to understand what would be the most appropriate technology to use. Now we'll spend a couple of minutes just talking about data management. So as we've seen an increase in deployment of instrumentation and an increase in amounts of data that have become available for tailings dam risk management, it's become very critical to have an effective platform. Here's a screenshot of our platform, for example, showing a tailings impoundment with a pressure contouring. So you can see this coloration on the left side of the screenshot. So instead of looking at individual instruments, which are depicted in that illustration by the red dots or the icons, you're now looking at your data in aggregate. So you're seeing with a single view, really the entire kind of pressurization view of the tailings impoundment. So this is one of the key features, I would say, of any data management platform now, and these are features we've worked hard to implement in our platform as well, is how you're going to make sense of these large quantities of data. We need these kinds of visualizations because nobody has time to be looking at individual charts anymore. And from a risk management point of view, it's a much more effective way to see what's happening in your facility. So again, this view is a split view showing this overall contour of the pressure, and then on the right side is this 3D chart. So you're actually seeing essentially like a 3D, like a phreatic surface. You're seeing in 3D the pressure surface internal to that embankment. So again, a much more effective way to understand the data compared to discrete charts of data. And then related to that, you have a lot of other data types that are being collected on the property. So for example, what about rainfall, or what about these different sources of radar data, or the prisms, or the in-place inclinometers? One of the other key areas of development for us in recent years with our platform is the ability to digest all these different types of data and then be able to present a 2D or 3D interface to allow for viewing these monitoring assets and really understanding kind of spatially where you're monitoring, what those monitoring assets are telling you, and ultimately where potential risks are developing in your facility. I won't spend too much time talking about this in favor of a brief demo. So let me switch over my screen share to a brief demo of our platform to illustrate how we can digest all these different types of data and present it in a compelling fashion. So this is a login to a demo database that we have running locally here in our offices. It is a client database, so the initial view, it's not their live database, but it's a copy of their database, which we're just using for demonstration purposes. This initial view is what's called a 2D view. So it's a map view showing the different monitoring areas for this large open pit mining operation, which consists of 2 pits plus several leach heaps and tailings impoundments. I'm going to switch to a second view, which is a 3D view. So it's essentially the same property, but rendered in a 3D view with all the monitoring assets shown where they exist in 3D space. When it first opens, it's shown as a like a partial view. I'm going to release that partial view and show the overall site view. So you can see as I move the mouse, I'm kind of navigating in space, showing the contours. There's several different layers actually viewable here, 3 different layers. So there's a surface layer, there's an internal fault layer, and then this green kind of this green overlay is actually satellite deformation data or InSAR data. So at a glance, not only do you see your whole inventory of instrumentation, but you also see where the satellite data has identified areas where you have movements developing. So for example, if I look at this leach heap here, which is around in the middle of the screen here, you can see some of these colored areas in this colored layer, which actually are starting to show some deformation, which you would expect in a leach heap or in a tailings impoundment. Then also you have a visual depiction of alarms. So you can see some of these icons are actually blinking. That indicates that you have measurements that are exceeding the thresholds that have been set. We have some tools for then being able to collect all this data and present it very quickly in a chart. So I'll quickly show you this. It's our selection tool for data. I'll click to set a base. I'll expand this little selection box. And you'll notice once I did that, it shows me which instruments are now within this box. And then on the right, it shows me a list of those instruments that have been selected. I can come up here to our charting tool and actually generate a chart for all the data that's within the bounds of that selection box, that 3D selection box. The chart settings by default were set to last week. This is not a live database, so we don't have data for the last week. But I went and set it to all the data that's available for those instruments. And you can see now it updates the chart. It shows me separate charts for all the different data types, which is a key feature with the charting tool. So now, whether it's your InSAR data, your ground-based radar, your piezometers, whatever you have in your monitoring inventory will now all be shown together in time synchronized view. So for example, on the top is shown our InSAR, and it shows for that given area that we selected the deformation that's occurred over time. You can see the scale here is showing up to 11 centimeters of deformation. And then in the lower chart, we have all of our piezometer inventory. So it becomes very easy to correlate the deformation data, the external deformation data, with other types of data, in this case, the internal pore pressure data that we're collecting. Okay, that concludes the presentation. Again, my purpose here was to give you an overview of the different technologies that are available, and then to give you an example of a platform that we've developed to provide for integrating the data, viewing the data, and understanding the potential risks that are developing in your tailings facility.
Thanks, Alex, for a great presentation. We have had a few questions come in from our listeners, so we've got a bit of time to do a Q&A session, if that's okay with you.
Sure.
I'll start now with the first question. So, what are the challenges to implement these systems?
I would say the two main challenges are cost and risk awareness. Miners in general tend to be pretty cost conscious. It's a tough business. Margins are often tight. Monitoring a tailings facility doesn't necessarily allow them to make more money. So there can be some pushback against the spending of money to monitor these facilities. Related to that, I think, is the risk awareness. The assumption is that these facilities, in the past, I would say, that these facilities are very stable, but the reality is there's many unknowns and failures develop over time. And so there is more awareness, I would say, by the mining community in general regarding the risks. And of course, we've seen some catastrophic failures in recent years. So that's really helped the industry, I think, to become more aware of the risks that can develop.
And we've got another one here. It's actually about costs as well. When you consider the costs for internal methodologies, what is the most cost-effective way to implement them?
Well, one of the challenges in general is that when you're looking at an existing structure, it's more expensive to monitor it after it's built. So, one of the ways to help mitigate the cost, especially for some of the internal monitoring, is to look at installing instrumentation during construction. It avoids using drillers. Drillers are very expensive to mobilize and demobilize and to be on the property. So anytime you can minimize the use of drillers, will save quite a bit in the cost of installation. We've seen cases where, it costs $200,000 for a really deep hole to install instruments in. And yet the cost of the instrument itself might only be a few $1,000s. So to actually do that installation during construction saves the cost of that drilling. So that's one of the key ways that I would say that you can minimize cost, is really looking at installing instruments during the construction of these facilities.
Great, thanks. If you had to choose one interior and one exterior methodology, what would you recommend?
Well, for sure, for interior monitoring, measuring hydraulic pressure is key. Failure happens in almost all cases because of water pressure building up and weakening materials. So you've got to have piezometers, I would say, is the key technology for internal monitoring. For external, I would say InSAR is probably the best tool for that. It provides large coverage areas. The good thing with InSAR is that it allows you to identify risk areas. So you may identify using InSAR an area that's less stable than you were aware. So then you can take a look at that area and then look at implementing other technologies like, say, a ground-based radar or prisms to provide more real-time monitoring. And failures in general, they happen over a fairly long period of time. So in the initial phases of monitoring, in the initial phases of construction, I should say, of a tailings impoundment, the risks are going to be fairly low. So having that program of satellite-based radar or InSAR will allow for monitoring over these large areas, potential failures over time.
We've got another one here. What are the differences between ground-based and satellite-based radars?
Yes, good question. I mentioned a few differences in my discussion on each of those technologies. Again, I would say the key difference is there's two key differences. One is the interval at which you can collect data. So as I mentioned, the frequency at which you're going to get satellite-based radar is anywhere between 1 and 11 days, depending on the service and the satellites and the area where you're operating. Whereas the ground-based radar, you can have data coming every 15, 30 minutes. So you have much higher data production. The other key difference is in the XYZ data. So satellite-based radar, because you're looking down, it has trouble with the horizontal surfaces. In many cases, it won't even provide any movement data if there's a lot of vertical surfaces. Whereas the ground-based radar is very good with those surfaces, and vice versa. Ground-based radar is pretty poor generally with vertical surfaces, but really good with horizontal. So those are the two key differences I would say between the technologies.
The video of the failure at the tailings facility in Brazil back in January showed an almost instant collapse. So what data collection intervals would you recommend for dynamic monitoring?
Well, it's important to keep in mind that while the video is very dramatic and it appears to be an instantaneous response, and yes, at that moment it was, the failure really developed over some period of time, weeks, I would say, maybe even months or years. And so really the interval, I would say, is not as critical as you would think. In other words, collecting data every second or every minute is really not going to be a good strategy. So I would say, really the most frequent interval we would ever see or recommend on a project is about once an hour. And you think about it from a risk management point of view. I mean, if you're collecting data once a minute, what exactly are you going to be able to accomplish in terms of risk mitigation if you've identified a failure that's occurring in 1 minute? There's really limited options at that point. So collecting data every hour, every 2 hours, or even, in some cases, even once a day, but over a long period of time will allow you to characterize those potential failure modes. And when they make themselves evident, you're going to have time to mitigate. And that's the key. That's the key to what you're trying to accomplish here with your risk management program, is giving yourself time so that you can actually mitigate a solution.
What is the total cost in terms of instrumentation and platform for a typical tailings dam deployment?
We get this question a lot. It's like the $64,000 question. It's really a tough question to answer because every project is different. And so, a budget that works on one project may not work at all for another. It may be too much or maybe not enough. So really, the overall design of the facility needs to be looked at. The height, for example, what are the risks that ultimately that you should be aware of for a given installation? A high impoundment is obviously riskier than a lower impoundment, but that's not necessarily even the case either, depending on how much material is being moved into these tailings impoundments. So there's really a number of different factors that have to be looked at. The design of the facility has to be looked at, what the potential risks are, and based on those considerations, a plan for monitoring can be derived from that. But it's very difficult, and I would say it would be a mistake to ever go into a project saying, well, this is our budget. Because really the budget should be whatever the project dictates. So once you've evaluated the risks, you can come up with an inventory of monitoring, and that's your budget. And so that's really the approach that we recommend to understand what the costs would be for a typical or for a given installation, I should say.
Great. I think that's about all we have time for now for the questions. I'd like to thank Alex Muir and Canary Systems for a really interesting and useful presentation and discussion. I'd also like to thank our listeners for taking the time to be with us today. Please do look out for the on-demand version of this webinar on the Mining Magazine website. It'll include both the audio recording and the presentation slides, and will be available to everyone who's registered for the webinar. So that will go up on the website in a few days. Our listeners are welcome to keep sending questions in, and we'll do our best to get some responses to you. So thanks again to everybody who took part in today's webinar with Canary Systems and Mining Magazine. I hope you enjoyed it.